Welcome to our channel Sankalp Study Success. Today in this lecture we are going to learn about Moore machine as well as Mealy machine. These machines are also known as automaton with output. That means automaton with output. That means both Moore machine as well as Mealy machine are going to have output along with their inputs. So here first let us discuss what is Moore machine. Here Moore machine, it is defined as a 6-tuple notation where m is equals to q sigma delta transition function lambda and q naught. Here q is nothing but the number of states, that is set of states, and sigma is the input alphabet where you are going to take all the input symbols, and delta is nothing but the output alphabet, which is nothing but all the output symbols. It includes all the output symbols, and as well as transition function, which is defined as q cross sigma tends to q. This is the transition function. Here lambda is the output function where q tends to delta. This is the output function which we define it as q tends to delta, and here q naught is the initial state. So we will define it as 6-tuple notation. This Moore machine. Now let us see what actually the Moore machine will do. Here Moore machine is a finite state machine. What finite state machine is nothing but DFA, that is deterministic finite automaton, right? In which next state is decided by the present state and present input symbol. Here in Moore machine, the next state you will decide with using present state and present input symbol, and output symbol depends on the present state. So if these two conditions are satisfied, then you can say that it is a Moore machine. The first one is next state is decided by present state and present input symbol, and output symbol depends only on the present state. So here how do you determine or how do you draw the transition diagram for Moore machine? Here for each and every state you will have each and every output. That means here the diagram which is drawn here is q1 by 1, q0 by 1. By 1, this 1 is nothing but the output. Here we are having output. So for q0 output is 1. So for q1 output is 1. For q2 output is 0. So these are the inputs which we apply generally, that is the same. But output is different. For each and every state we are having output of 0 and 1. So in case of Moore machine, if the length of the input string is n, then the length of output string becomes n plus 1. So in case of Moore machine, if you are having the length of the input string is 5, then the output string length will be 6. If in case the length of the input string is 10, then the length of the output string will become 11. So like this, the input and the output will vary in the Moore machine. So let us solve some problems related to Moore machine, which are design a Moore machine to count number of B's in a given input string with A's and B's. That means input string consists of A's and B's. That means input alphabet is equals to A comma B. And here we have to count the number of B's. That means how can we design a Moore machine? See, if there is a transition from one state to another state by applying B, then let us take the output as 1. If we are having a transition from one state to another state by applying A, then we will take the output as 0, because at the end number of ones will be equals to the count of number of B's, right? Because we are representing B's with ones and A's with zeros. So number of ones will become number of B's. That means what? Here let us draw the diagram first, which is q0 is the initial state and we have to count the number of B's. That means if a B is going from q0 to q1, here the output will become 1. Because for each and every B, we are counting each and every 1. That means here we have applied B. Now let us give a self loop on q1 so that for every time B is going to be iterated, for each and every time we will get the output as 1. So we are going to count the output. Here, if it is A, because we are having both the input symbols A's and B's. So if it is A, then the output becomes 0. And here we have applied B, because as it is a finite state machine, Moore machine is a finite state machine, that is nothing but DFA. So we have to apply all the input symbols to each and every state. So here we have applied B but not A. So if A is going to be an input symbol, then the output must be 0 according to our logic. So here the output is 0. So from Q1 to Q0 there is a transition by applying A. So in this way we are going to design a Moore machine. So let us take a valid. Now we are going to draw the transition table for the Moore machine which we have drawn. That means what here? Present state. The next state is A comma B. That means there are two input symbols. Then this is the output. Now what is the present state? Q0 and Q1, where Q0 is the initial state. Here for Q0, if you apply A, then it moves to Q0. If you apply B, then it moves to Q1. For Q1, if you apply A, it moves to Q0, and if you apply B, it moves to Q1. So the output for Q0 is 0 and the output for Q1 is 1. So in this way we are going to draw the transition table in the case of Moore machine. So in case of Moore machine, we are going to take the present state, the next state and the output for each and every state. So now let us see whether a string we are going to count the correct number of B's or not. That means let us take a valid string, which is, let us consider ABA double B. Now we are starting from Q0. If you apply A, then it moves to Q0. If you apply B, then it moves to Q1. Then apply A, because according to the string which we have taken, we are going to process in the same way. So for Q1, if you apply A, it moves to Q0. And if you apply B, it moves to Q1. And if you apply B, it moves to Q1. So for each and every state, we are having outputs. For Q0, it is 0. For Q1, it is 1. Q0, 0. Q1, 1. And Q1, 1. How many number of 1s are there? Those many number of B's are in the input string which we have taken. That means there are 3 1s here. That means there are 3 B's in the input string. So there are 1, 2 and 3 B's. So that means the machine which we have drawn is exactly correct. So in this way we are going to draw or design a Moore machine for the given appropriate question. So in this case, counting the number of B's is nothing but getting the number of 1s as output. You can also consider getting the number of zeros for B's and number of 1s for A's also. So in that case, number of zeros will be equal to the count of number of B's. So let us solve one more question where design a Moore machine to generate 1's complement of given binary number. That means what? Any binary number if you take, 1's complement of that number should be the output. So in this case, now let us consider sigma is equals to 0, 1 because it is a binary number. So now if sigma is equal to 0, 1, if you take the complement of the number, that means the output will be also in the binary format. So delta is equals to 0, 1. Now let us draw or let us design a Moore machine from initial state. We are going to draw it for the initial state. Now from the initial state I am going to Q1 by applying 0. That means if I apply 0, then I have to get the complement of 0, that means 1. Here output of Q1 will become 1 because the transition from Q0 to Q1 by applying the input symbol 0. So now if this is 1, then I have applied 0. If I apply 1, I am going to another state here. I have applied 1 here. That means I will get the output as 0. I should get the output as 0, correct? Because if I apply 1, then the complement of 1 is 0. So in this case, I have to get 0. So now, as it is a DFA, we need to apply all the input symbols to each and every state. Here, if it is 0, then I can come from Q1 to Q2 by applying 1, because here the output is 0. And I can go from here to here by applying 0 to get 1. Correct? And now, for Q1, we have applied 1, but we didn't apply 0. So, you can take 0 as the self loop here, so that we are having 1, and here you can take 1 as the self loop, so that we are having 0 as the output. And here you can take the output as 0, because there are no transitions coming to Q0 from another state. So in this way we are going to design a Moore machine. For this Moore machine, let us draw the transition table, whereas present state, next state which is 0 and 1, and the output. Present state is nothing but Q0, Q1 and Q2. For the next state, that means Q0, if you apply 0, we are going to Q1. If we apply 1, we are going to Q2. Q1, if you apply 0, it goes to Q1, and for 1, it goes to Q2. For Q2, if you apply 0, it goes to Q1, and if you apply 1, it goes to Q2. So the outputs of each and every state are 0, 1 and 0. So this is the transition table for the Moore machine. Now, in this way, we are going to draw the Moore machine to generate 1's complement of the given binary number. Now, let us see a question of different model, which is construct a Moore machine to determine residue modulo 3 for binary number. That means what? We are going to take the binary number, output and input is the binary number. That means sigma is equals to 0, 1, because binary number just consists of only 2 digits, 0 and 1. Here residue modulo 3, that means for the binary number, if the number is divisible by 3, then residue modulo 3 is nothing but number is divisible by 3. Divisible by 3 means the reminders are 0, 1 and 2. So these are nothing but the outputs. So here, if you take 0 to 9, 3, 4, 5, 6, 7 and 9, 8 and 9, then by converting into binary format, 101, 110, 111, 1000 and 1001. So if you mod 3, if you do mod 3 for each and every number, then you will get the reminders as 012, 012, 012, 0. So reminders are 0, 1 and 2. That means we are going to have only minimum states are 3. That is Q0, Q1 and Q2. So Q0 is the initial state. Now if 0 is accepted, then the output should be 0. That means there are any number of zeros, right? Any number of zeros can be accepted with 0 as output. So this is the input and this is the output. Now 0, 1 should be accepted. That means here there is a 0 already, and here if you apply 1, then this output should become 1, right? Because for 1, the output is 1. So if you process 0 and 1, you have to get the output as 1. Now if you process 1 and 0, that means here we have 1. If you go from Q1 to Q2 by applying 0, then the output becomes 2, because it is 1, 0 and the output is 2. Now if you take 1, 1, then the output should be 0. Here we have 1. For every iteration, we are going to start from the initial state. So here we have 1 and output is 0 in this case. So if you come back with 1, then the output is 0. Now 1, 0, 0. That means we have to get the output as 1. 1, 0, and if you come back with 0, then you are having the output as 1. So like this, we are going to apply for each and every state. And here 0 and 1 is applied to Q0, 0 and 1 is applied for Q1, 0 is applied to Q2, but not 1. Let us see. 1 for 5, the output is 2. For 1, 0 and 1. If you come back to Q2, then the output is 2. So in this way, we are going to draw Murray machine for residue modulo 3. That means we have to take the residue modulo 3 and we are going to get the reminders. Then we are going to draw the transition diagram for Murray machine. Now you have to draw the transition table for the Murray machine like this. Present state, next state with the input symbols of 0 and 1 and the output. We are having 3 states Q0, Q1 and Q2, where Q0 is the initial state, Q1 and Q2. If you apply 0 to Q0, it is going to Q0 and 1, then it is going to Q1. For Q1, if you apply 0, it goes to Q2 and Q0. And for Q2, if you apply 0, it goes to Q1 and for 1, it goes to Q2. That means Q1 and Q2. So the outputs of Q0, Q1 and Q2 are 0, 1 and 2. In this way, we are going to draw the transition table. So this is about Murray machine. Now let us discuss what is Mealy machine and let us solve a problem of Mealy machine. Here the first one is what is a Mealy machine actually? Here the next state, it is decided by the present state and present input symbol, and also output symbol depends on both present state and present input symbol. Previously, in the Murray machine, output symbol only depends on present state, but here output symbol depends on present state and present input symbol. So this is the difference between Murray machine and the Mealy machine. Here also we are going to have 6 tuple notation, the same notation of Murray machine, where Q is the set of states, sigma is the input alphabet, delta is the output alphabet consisting of output symbols, and this is the transition function, where transition function is defined as Q cross sigma tends to Q, which is same as Murray machine. Q cross sigma tends to Q, and here lambda is the output function. In the same way, it is Q cross sigma tends to Q because output symbol depends on present state and the present input symbol. So it depends on both. That's the reason it is Q cross sigma tends to Q. So in this way, we are going to define Murray machine as well as Mealy machine. Now let us see how do we draw Mealy machine. Here, as the output depends on present state and present input symbol, for each and every input symbol, we are going to have an output. That means here Q0 is one state and Q1 is another state. There is a transition from Q0 to Q1 by applying 1, which is having an output 0. That means the left side 1 is the input and the right side 1 is the output. So like this, we are going to define input and output for the given transition function. So for each and every input, there is an output. That means the transition table goes like this, whereas the present state is nothing but all the states which are included in the transition diagram, and the next state and the output. Where are we going to the next state if we apply 0 and if we apply 1, and what is the output for that input? We are going to specify in the transition table. Now, here, previously in the Murray machine, if the length of the input string is n, then the length of the output string becomes n plus 1. But in Mealy machine, if length of the input string is n, then length of the output string is also n. In this way, we are going to specify the Mealy machine. Now, let us solve a problem related to Mealy machine. Here, design a Mealy machine which can output symbols E or O. That means even or odd. According to total number of ones encountered is even or odd. That means here sigma is equal to 0, 1. But the outputs are E or O. That means you have to specify whether number of ones are even or odd. That means let us start with an initial state Q0, and here there is another state Q1. If you move from Q0 to Q1 by applying 1, then there is only one 1, right? That means we are having odd number of 1s. So here, if we are moving from Q1 to Q0 by applying 1, then here it will become even, right? Because here it is odd. If it is 1, 1, it is odd. If it is moving 2 times, then it is even. If it is moving 3 times, then it is odd. That means we have to count the number of ones and say whether the number is even or odd. So here Mealy machine is also a DFA, right? Deterministic finite automata. That means we have to apply both the inputs for each and every state. Here you have applied 1 and now you need to apply 0, where if you apply 0, then number of ones are nothing but even, right? Because there is no 1. 0 ones. 0 is also an even number, so that is even. Now here we have applied 1, but we didn't apply 0. If you apply 0, then here you will get the number of ones as odd, because here there is only one 1. That means it is odd. So in this way, you have to take whether the number of ones are even or whether the number of ones are odd. Now let us draw transition table for Mealy machine, whereas the first one is the present state. Here the input, it is 0 and input of 1. Now what is the next state if you apply the input 0, and what is the output for that? Let us specify in this way. This is the next state for the input 1 and for output. So for the present, there are only two states, Q0 and Q1. For Q0, this is the initial state. For Q0, if you apply 0, then the next state is nothing but Q0. Because if you apply 0, it is coming to Q0. So output is nothing but E, that is even. So for Q0, if you apply 1, it is moving to Q1 and the output is O, that is odd. For Q1, if you apply the input 0, that is, it is moving to Q1 and it is odd. And if you apply 1, then it is moving to Q0 and the output is even. So in this way, we are going to draw the transition table for the Mealy machine here, right? Now let us take an input string where 11011, right? This is an input string. Here the number of ones encountered are even, because there are 4 number of ones, which is an even. So now let us trace it out whether we are getting the even or odd. First, starting with Q0, by applying 1, we are going to Q1. If you apply 1, it is coming to Q0. If you apply 0, it is at Q0. And if you apply 1 for Q0, it is going to Q1. Then if you apply 1 again, it is moving to Q0. Now, what are the outputs? Q0, if you apply 1, let us write the outputs here in this box. For Q0, if you apply 1, then it is odd. For Q1, if we apply 1, then it is even. Then the next one is even, odd and even. So now which output is our output actually? That means the last symbol which we get, that is the exact output of our input string. That means we got even. Even, that means what? Here the number of ones in the input string which we have traced out is even. So in this way, we are going to solve the problems of Mealy and Mealy machine. So thank you for watching the video.